Welcome to my presentation on the 1986 Nobel Prize in Physics, the scanning tunneling microscope. Gerd Binnig and Heinrich Rohrer won the half of the Nobel Prize in Physics in this year, and they wrote in an article, "A new kind of microscope reveals the structures of surfaces atom by atom. The instrument's versatility may extend to investigators in the fields of physics, chemistry, and biology." Even if the scanning tunneling microscope is not a microscope in the traditional sense, the main difference to all other microscopes is that it does not use free particles for imaging. Therefore, no lenses or special light or electron sources are required. And with the help of this microscope, the surface can be made visible atom by atom. It is even possible to resolve structures that are about 1/100th the size of an atom. It is an important tool for research in various fields, as in biology, physics, chemistry, medicine, and it is also of great importance for the microelectronic industry. On the right, we see a large scanning tunneling microscope in the labs of the London Centre for Nanotechnology. Though about the content, first I tell you something about the history of microscopy. Then I introduce to you the Nobel Prize winners Gerd Binnig and Heinrich Rohrer. Then we have a little bit to talk about the theoretical basics, the quantum tunneling. Then I show you the setup and the functionality of the STM. Then I tell you something about the surface science, especially the silicium-111 7x7 surface, and then I show you other scanning tip microscopes. The scanning tunneling microscope is a product of a long, considerable evolution. The microscopy has already started in the 15th century when the geometrical optics leads to production of telescopes and simple magnifying glasses were produced for observing insects, and this became very important in many fields of natural science. In the 17th century, Anthony van Leeuwenhoek developed the first light microscope. That revealed the existence of single cells, pathogens, and also bacteria. However, optical resolution is limited by the average wavelength of visible light, which is up to 2,000 times larger than the diameter of an atom, which is in the order of only a few angstroms. Because of this, it is not possible to resolve atomic structures. It was the discovery and the development of quantum mechanics and the associated wave nature of electrons that made it possible to develop the electron microscope. Ernst Ruska was awarded the other half of the Nobel Prize in 1986 for his fundamental work in electron optics and for the design of the first electron microscope. And with this instrument, it was now possible to resolve regular structures within crystalline materials. But the surface structures still posed puzzles, because due to the high speed of the electrons, they penetrated deep into the structure and only gave information about the inner structure. The properties of the surface of a solid differ radically from those of the interior. For instance, to minimize energy, surface atoms often arrange themselves differently from the other atoms in a solid. And in the 1980s, Gerd Binnig and Heinrich Rohrer developed the STM at the IBM Zurich Research Laboratory in Rüschlikon. Now I tell you something about two of the Nobel Prize winners 1986, Gerd Binnig and Heinrich Rohrer. On the left side there you can see Gerd Binnig. He was born 1947 in Frankfurt in Germany. And on the right, Heinrich Rohrer. who was born in 1933 in Buchs in Switzerland, but he died in 2013 in Wollerau. They both worked in Rüschlikon at the time of the award, as I mentioned before, and the original idea at that time was not to build a microscope, but to do spectroscopy locally on an area less than 100 angstroms in diameter. They were particularly interested in inhomogeneity on surfaces, especially thin oxide films on metal surfaces. However, a suitable tool was lacking. The two Nobel Prize winners had the idea that tunneling, which was already discovered a quarter of a century earlier, might offer new insights. It soon became clear that this was not only the idea for a local spectroscopic probe, but also that this tool would provide spectroscopic and even topographic images. In other words, a completely new kind of microscope. The underlying idea of this new tool is the tunneling through potential barriers. If one considers classically a particle, for example an electron, with a certain energy and a potential barrier with a higher energy than the particle, then the particle cannot pass this obstacle. But quantum mechanically, we consider the particle as a wave and no longer as a point which has a measurable position and a velocity at any time. It is a wave function which is a solution of the Schrödinger equation. One can indicate only a probability with which the particle, respectively the wave, is in a certain space area. And this probability is not zero within a finite barrier as one would expect classically. It decreases exponentially within the barrier. And we can see it on the right, where we have a wave package and a barrier with a higher energy than the wave package. And we see beyond the barrier we have also amplitudes from the wave packets. The probability to find the particle beyond the barrier is not equal zero. How big the probability is that a particle tunnels through depends in principle on the thickness and the height of the potential barrier. And this phenomenon has been used by the researchers Binnig and Rohrer. The idea of their microscope is based on the fact that through a barrier created by a vacuum or a gas or a liquid, which acts as the potential, electrons tunnel through and generate a measurable current. The first experimental verification of tunneling was made a quarter of a century before by Eva Schäfer of the General Electric Company, where a thin, rigid insulating layer was used to separate two electrodes. The gap between the electrodes was small enough to allow the electron clouds to overlap slightly. A potential difference between the electrodes induced by applying voltage to them causes electrons to flow from one electrode to the other. Now we come to the setup and the functionality of the STM. To build the first STM, the already known standard tunnel configuration containing the two electrodes separated by an insulating layer was slightly modified. One electrode, here the blue one on the bottom, was replaced by the sample, but this also means that one surface to be investigated has to be conductive. The other surface is replaced by a very thin, at its best single atomic, scanning needle tip. The most commonly used tip materials are tungsten, platinum, or platinum iridium wires. The gap between is often empty, so ultra-high vacuum. It can also be filled with the atmosphere, but there is a problem that this contains oxygen, which can oxidize the surface or change the surface in other ways. The measurement can also be done in a liquid. The advantage there is that the sample does not change by contact with air. This is certainly the case for some biological samples whose natural environment is a liquid and which will collapse if it dries. By applying appropriate ramps to the X and Y piezo drive, the tip is scanned along the surface and follows its contours. So therefore the word scanning in the scanning tunneling microscope. And the piezoelectric ceramics are used as the actuator. They combine a large scanning range with a minimum deflection in the sub-angstrom range. The underlying piezoelectric effect is a generation of electrical polarization by applying stress to a crystal. It also works the other way around. These ceramic cylinders change their length. They are enlarged or reduced when an electrical voltage is applied, so when current flows. And this property is used to adjust the position of the metal tip very precisely on the one hand, and on the other hand, to keep the metal tip at a constant distance from the sample. The piezo bars move the tip in a straight line over distances up to 10,000 angstroms. Furthermore, this movement is very sensitive to the level of applied voltage. A voltage of the order of 0.1 volts results in a movement of 1 angstrom. This precision of the drive of the tripod is so good that currently only vibration limits the vertical resolution of the sample surface. This resolution is currently in the range of a few hundredths of an angstrom. At the junction, a constant voltage is applied, a few millivolts up to a few volts. A control unit regulates the C piezo drive in such a way that a preset current, several hundred picoamperes up to several nanoamperes, is established. Any change in current will be corrected by a feedback signal to the piezo drive, which will position the tip at a constant current level above the surface. So the tip is scanned along the surface and follow its contours. The feedback signal yields directly to the topography of the surface, as you can see on the figure on the right. Besides the constant current mode, there are further modes, like for example the constant high mode. An advantage of this is that it can scan faster, even produce real-time images, but there is also the risk of a collision with the surface of the sample. You can also do spectroscopy, which was the original idea of Pinnick and Rohrer. As already mentioned, vibrations are one of the technical challenges that had to be overcome. An important source of vibrations are resonances of the building where the scanning tunneling microscope is located, but also sound and the response of the system to these disturbances. The simplest solution is to place the STM in a quiet part of the laboratory and measure at quiet times. This is even more effective if the STM is operating in a medium that carries sound waves. But a better way to reduce external vibration sources is to install a vibration isolation mechanism. There are 3 types of isolation which were used for the STM. The first STM used magnetic levitation of permanent magnets on a superconducting lead shell, but this method is not longer used today. Another method was to suspend the STM with spiral springs. These springs act like a low-pass filter. Up to the cutoff frequency, the STM follows the movement of the coil suspension. However, there was a problem that at the cutoff frequency a resonance occurs, which should be suppressed with the help of damping, for example an eddy current damping. A disadvantage of damping is that it reduces the performance of the conductor at higher frequencies. A third method of vibration isolation consists of several stacked metal plates separated by Witton plates, which acts as springs and dampers. A typical compression of these plates is 1 millimeter, which corresponds to a cut-off frequency of about 16 Hz, if it is assumed that the Witton plates adopt a harmonic behavior. This value is higher than that which can be achieved with a spiral spring system. So it's the most common one. Now I tell you something about the surface sign which can be made with an STM. One of the most common and best studied materials with the STM is certainly graphite. Here on the right you can see the graphite structure. Graphite has layered honeycomb structure. One half of the atoms lies directly above the atoms of the underlying layer, as you can see here in black, and the other half lies exactly in the middle of the honeycomb in the holes here in red. Graphite has been studied in many different arrangements by a wide variety of researchers. In ultra-high vacuum, under water, in air, in liquid helium, under oil, and so on. Furthermore, with the help of the STM, we can study metals and also non-regular structures, adsorbate covered surfaces, conductors, semiconductors. And if the action can be performed in a controlled way, today it is even possible to modify a conducting surface with the tip of the STM, where material can be transported from the tip to the sample and back. A popular research object of the scanning tunneling microscope are semiconductors, as I mentioned. In particular, the study of the complex silicium-111 7x7 surface. This diamond-shaped unit cell of silicon is called 7x7 because each of the 4 edges of the cell measures 7 atomic distances. You can see it on the right. Each 7x7 contains 12 bumps, which could not be visualized up to this point, and each bump corresponds to a single atom. The bulk layer within a silicon crystal is shown on the left, and this unit cell contains only 2 atoms. This purple area is a 1-1-1 intersection. There were some impressive experimental and theoretical efforts dealing with the structure of these reconstructions until the construction of the first scanning tunneling microscope. Because of the very large unit cell, which you can see here, it was difficult, if not impossible, to obtain the current structure from a wide variety of different experiments, and the models from some of these experiments seems to conflict with those obtained from other experiments. A new approach to this problem was the development of the STM, and Rohrer and Binnig addressed this issue. The first STM observations in 1982 immediately ruled out a number of proposed models. To test various proposed models for the 7x7 reconstruction, theoretical STM images were calculated for each of the models. A spherical charge density was assumed at the center of each atom, and the most likely one was the DAS, the dimer adatom standing fault model, which was consistent with the results of other experiments too. So on the right, I said we can see the 7x7 unit cell, and with A there are the adatoms. The rest atoms are have a little r, And C are the Kolmar rest atoms. From the STM, other types of microscopes have evolved, such as the atomic force microscope. With this hybrid of scanning tunneling microscope and stylus profilometer, it is possible to examine insulators on atomic levels without damaging the sample. STM and AFM can also provide information on the microscopic roughness of a surface. Friction force can be measured very sensitively with a high spatial resolution. Therefore, it is now possible to understand friction on the atomic scale. Other scanning tip microscopes are the scanning thermal profiler, which uses the conduction of heat from the tip to the sample via the air, which depends on the properties of the air. Another one is a scanning noise microscope, which uses the fact that a tunnel junction produces noise, which is related to the current, which itself depends on the tunnel resistance. Generally speaking, it is impossible to use an STM on an insulator. The nonlinear alternating current tunneling microscope uses the third harmonic to detect the tunnel current even in insulators. The second harmonic is not useful because it's zero, because the current curve is symmetric. There are also a scanning ion-induced microscope or a detection of secondary particles possible, or the ballistic electron emission microscope to explore different surfaces. Even though the scanning tunneling microscope turned 40 years old last year, it is still an important research tool. Scanning tunneling microscopy has proved to be an extremely powerful technique. It can give topographical and spectroscopical information on sub-nanometer scale. Its imaging capacities are used in a broad range of scientific and technological applications. Some of these are already well established, other areas are still evolving.